thick jacket. So, hello everyone. Today, as Carl was saying, I'm going to talk about how we can bring RQI a bit closer to experiments, so bring it into the lab. And one of the possible experiments would be doing entanglement harvesting. And so first, I want to acknowledge the collaborators in this project because it takes quite a bit. And first, there is my group is the theory group of Barry RQI with my supervisor Eduardo Martinez. And then the group without this experiment would not be possible is the superconducting quantum devices group at IQC. And this is led by Adrian Lupascu and students of his, Elena Kornick, Lucas Hack, Noah Jansen, Shidai, two of which are here in the audience, and Lucas Hack and Noah Jansen up there. And there is also other students from Adrian Lupascu that work on this in the past, and master students like Shihao Ji and Sean Ren. So first of all, today I'm going to go first on why we want to do these experiments, how can we use superconducting devices for this, and we also look into, in theory we have the Unruh-DeWitt model, we also have the experiment, the superconducting devices that can do the experiment, but we can have an intermediate step between these that can bridge the gap between these two different scenarios. And then what would be the consequences of this intermediate model for an entanglement harvesting experiment? And we'll finish afterwards. Okay, so first, why do we want RQI experiments? Obviously, in RQI, we usually use theoretical tools, mainly the Unruh-DeWitt detector that appeared a lot today. There were great introductions about it before lunch, like from Mateus and Bruno. And also, these Unruh-DeWitt detectors, we use them for a myriad of applications that also appeared today: entanglement harvesting, Unruh radiation, or exploring black holes or curved spacetimes. But these tools, we already can explore all these scenarios. So why would we want to have an experiment? Well, first, of course, to verify these predictions that RQI has, like actually perform them in the lab. And then, because experiments can bring us to places where theory cannot, like having regimes with strong coupling, where it is not non-perturbative, so we cannot do many calculations there. Sorry. So why why the superconducting circuit is one method of doing these experiments, and why are they useful? Well, first, they are very good technology, superconducting circuits. This has been developed already in the 1999. The first qubit was done for quantum superconducting circuits. And since then, control over these qubits has improved a lot. And right now, there's a recent article even with qubits that can last for a coherence time of 1 millisecond, which is actually impressive. And also then, the fabrication of these devices is as chips, which is a widespread technique. And relatedly, the largest quantum computing currently is with superconducting circuits. And it's 433 qubits of IBM. So it's a powerful technology. And but being powerful is not enough. We also need characteristics that allow us to make RQI devices. And mainly what researchers here in IQC were able to do in Adrian Lupascu group was to, like last year, they put out this article in arXiv, which is long title, but basically it consists of a tunable coupler, so we can change the coupling between a two-level system, so a qubit, which we are very much used to use, and a waveguide, which is basically equivalent to a one-dimensional quantum field. And we can bring this qubit and one-dimensional quantum field from decoupled to strong coupling, so very strong coupling regime. This is what the superconducting devices team were able to do. And this interaction, we were able to turn it on and off very fast in the matter of nanoseconds. So this is actually great to do an experiment like entanglement harvesting, because we need, if we want to make the most impressive claim, we want to have space-like separated interactions that get two qubits entangled, even though they did not have time to interact between them. So very fast turning on and off of the interaction is needed. So here to have just an image of what is the actual device that they built in the lab. This would be only one detector, one particle detector. This is on the left, I think the pointer, oh yes. There's lots of elements of it, but there is mainly the qubit loop, so a two-level system, which is coupled to the transmission line, which here only appears a little bit, but on the right-hand side, you can see a zoom out. The transmission line is long, goes from one side to the other, and the other lines are control that allow you to change this intensity of the coupling between the transmission line and the qubit. So, yeah, and this was the image from their article. And so now, what is this circuit made of? Let's go start with the simplest element, which is the core of every superconducting circuit, which is the Josephson junction, which is surprisingly simple but very powerful. And it's basically superconducting, two superconducting bits, which are separated by a gap or an insulator. And what makes this special is that these two superconducting parts can couple to each other through tunneling. So charges, like Cooper pairs, can tunnel from one superconductor to the other. And this coupling allows for qubits and all the tunable coupling that we have, I have mentioned before. And now just to use this in the next slide, I will use this diagram to represent the Josephson junction. This is just a cross on a cable, a superconducting cable, and represents this here up there. So this, which is pretty much more complex, is the actual full device. This would be one particle detector. And we have to go step by step. We have here on top the waveguide. So this is the one-dimensional quantum field. And here at the bottom, we have what in the superconducting devices research is called a flux qubit. So here, this would work as our two-dimensional level system. And in between them, there is this tunable coupler. And all over it, there are the Josephson junctions from the previous slide. And so here, just with Josephson junctions, we cannot achieve any variable coupling. In order to be able to control this, there is another element in this picture, which is here this F beta and F epsilon, which are actually external magnetic fields that go through these loops here, through this loop of the bottom and loop on the top. And through this, they were able to change the coupling between this qubit and the waveguide. And in this matter of nanoseconds that I was saying before. Okay, so all this circuit is certainly more complicated than a Rude-Witt detector. The Hamiltonian of that circuit is, I did not include it here, but it's quite longer. So using that for a theory, it would be complicated. It's not good for analytic calculations, as the Rude-Witt detector is, but it's what we actually need to get an accurate model of the experiment. So there's some work from the Adrian Lupascu group, like from Shi-Dai, which modeled the Hamiltonian of the system, and were able to extract the energy levels of the Hamiltonian through numerics. You need to do numerics. And they analyze the Hamiltonian. And then for each of these parameters that can be turned as a knob in the experiment, he can add the energy levels, the lowest ones, which is the ones we care about, and the coupling strength between these energy levels and the waveguide, which is what we also care about. Okay, so these, when we get these outcomes of the code from Xi, this uses several energy levels. But if we want to get something more simple, a simpler model, we can restrict ourselves to the two lowest energy levels of the superconducting detector. So we actually look into a qubit. And this is a valid approximation, just looking at the lowest energy levels when the interaction of the qubit, like the change in the coupling intensity, is low enough over time. And slow enough, I mean slow enough compared to the energy gap. And specifically, more importantly, to the energy gap of the higher energy levels. And also, another feature that comes out of this numerical diagonalization that I was saying before is that the gap between the energy levels depends on the intensity of the coupling. So this is just an expression for the coupling that we can change over time, and the gap of the detector actually has a constant term when it's uncoupled, but there is also a variation proportional to the intensity of how strongly coupled the qubit is to the waveguide. So this is a feature that we usually don't have in Rudewitz detectors, and we would like to include it. As we're looking here, which is these two features that I have described, or all the features, some features of the experimental model can be added to the Rudewitz detector, so that we have a model that's closer to experiments, but still not the full Hamiltonian of the superconducting device. And this would be having this variable gap that I was just mentioning. And then the detector actually is considered point-like in the experiment, because what dominates over the detector size is the cutoff of the field. The modes are attenuated when they are very high frequency, and this is actually the main contribution. And the last thing is that instead of coupling to the amplitude, that is the most common choice for Rudewitz detectors, it's coupled to the spatial derivative of the field. So here below is the summary of this as a Hamiltonian of the interaction. And we have the coupling constant. This chi of x is the switching, which is basically our dependence over time of the coupling. And a monopole moment, an operator on the qubit, and the derivative of the field at the point where the qubit is. And this is just to represent that the monopole moment now has a variable gap. So it has a more complicated expression that involves the integral. So this model now, why do we care about it? It's because I was saying before, this model is closer to experiments while still being amenable to analytic calculations, or at least easier numerical calculations, which is what we have to use. And we can look specifically at this new feature of the experiment of having a variable gap separately from all the complexities of the experiment involves. And so we can better understand what this new effect can have over performing experiments such as entanglement harvesting. This is what I'm going to show next. This model on entanglement harvesting, what can it tell us about an experiment? Is first just to have a setup of the entanglement harvesting is, as has appeared before, we can have two detectors that interact in space-like separated regions, detector A and B. And even if this interaction is space-like, they can get entangled. But there is no current experimental realization of this. And that's what, in the future, we want to do with the experimental group here in IQC. And the model, the intermediate model that I was saying before, that has the variable gap, has the following effects that are here in these plots. Basically, if we consider these two detectors to have a Gaussian switching, which is, and the cutoff of the field to be very slow, so the mode's intensity decays very slowly with frequency. And we measure the negativity of the final state of the two qubits. And here I plot the log base 10 of it. And the warmer colors are higher negativity, this is lower negativity. And here is the usual scenario where we are used to. there's more harvesting. At the horizontal axis is the separation between qubits, and the vertical axis is the time that the interaction takes. And the longer the time interaction, the farther you can get entanglement from. But once you add the variation of the gap over time, in this case we look at the gap that when the detector is fully coupled reduces by 20%. So it's a considerable, even not huge reduction, but already has an effect that can be seen in this plot. And basically it's harder to get entanglement far away when there is a variation in the gap, but the entanglement is actually easier to get when you have your detectors close. And with this, I just want to finish and go a little bit over everything. The first, the development that the team at IQC were able to do of having a tunable coupler can allow us to, in the future, have RQI experiments in the lab and explore new regimes. And we can also get an intermediate model so that we can understand better experiments by adding the gap variation over time to the Andrew-DeWitt detector. And in the future, we would want to have a full model of the experiment, the evolution over time of the superconducting detector and field. But this requires a lot of numerical computation, which we are still working on. And finally, with these numerical results, better design the parameters of the experiment to get entanglement harvesting from space-like separated regions. With this, I thank you for your attention.